Hello, my name is Mahmoud Mahnasi. Today I'm going to represent you our work on using machine learning to generate network configuration. This work has been done within Huawei, Canada, in Waterloo Research Center. First, I would like to define what is network configuration. Network configuration could be defined as the process of acquiring, organizing, and maintaining information about all components of computer network. This process is usually done manually, which is a very tiresome and very complex, which is a very complex operation and very error prone. For example, in 2017, Google has leaked some prefixes which causes a which knocked off Japan from the internet. Another incident happened that causes New York stock market to close completely. In 2015, similar incident happened for Facebook and United Airlines that causes some airplanes to land unexpectedly. In this slide, I'm going to represent you an example of network configuration, network misconfiguration. For example, in a data center network, when we have multiple sub-networks, each one has its own prefix, and these networks was announced using the gateway router after aggregating all subnetworks masks in one big prefix, as we can see here. And the ISP was providing this data center with a default route. If one of these subnetworks fails, then the gateway router keep aggregating all prefixes in one prefix, as we can see here. Therefore, the ISP will keep forwarding traffic for this failed network through the gateway, but the gateway router won't be able to find a route for this traffic, so he will bounce it back using the default route that's coming from the ISP, and the ISP will keep forwarding it again to the gateway, and the traffic will keep bouncing between the ISP and the gateway router. Therefore, we can see this is not the desired behavior, and this mistake cannot be seen from the first configuration because it has been triggered when a failure happened in the network. Similar BGP misconfiguration happened for other scenarios. To address this kind of misconfiguration behavior of BGP, three approaches has emerged in the literature. The first one is to verify the existing configuration, as we can see in Backpipe and RCC and ARC. These techniques basically use a predefined verification scenarios on the existing configuration, which has been done written manually. Another approach is to fill out existing network templates, and in this approach, they basically have a template for certain network topologies or a certain network configuration, and they use an automated mechanism to fill out these holes with appropriate parameters. Another approach which tries to generate the full network configuration, and in these approaches they basically generate either an SMT model of the whole network or an automata or use automata theory for the network topology and generate a full configuration of the network. In our approach, we try to generate the full network configuration. However, we use the advances that has recently emerged from deep learning and neural network. Our approach we called DeepBGP. Basically, we have four components. The first component is a graph neural network (GNN). The second component is the configuration writer. The third component is an ES optimizer, the evolution strategy optimizer, and the third component is the configuration writer. We also feed the intent from the network as a YAML file, as we can see from the input here, and we encode this intent into the network and into the GNN feature or label matrix directory. To illustrate the working mechanism of this behavior, we can see here that we start with the network topology and with the intent expressed as an YAML file. And then we feed this, we take that network topology, we generate two layers of this topology. The first layer for the interior gateway protocol layers. The second one is for the exterior gateway protocol. Then for the interior gateway protocol, we basically we're basically interested in creating a full connectivity between all nodes, and therefore we used RIB protocol in our research. However, for the exterior gateway protocol, we are interested in establishing the operator intent, as we can see from the YAML file. Therefore, we've taken the YAML file, we encode it in the labels for each node. For example, label AS200 can reach AS100, can reach itself, cannot reach AS300, cannot reach AS400, and can reach AS500, which is the internal autonomous system here, the orange big autonomous system. After this encoding, we collate this information and we generate the label matrix, as we can see here, for all nodes. For example, we can also encode a more complicated scenarios, for example, as if the autonomous system 200 prefer router B over router C, and we can see here that 200 prefer router B over router C to reach a certain destinations, as we can see from the value here. And then we apply the GNN for this information. Basically, the GNN, what it does, it aggregates a feature from all nodes and pass them through a neural network and generate the feature of the output nodes. For example, as we can see in this figure, to generate the feature of node A, we aggregate the feature of node C and E to get the information of node D. As you can see, feature of C and E gets as an input for the neural network and generates the feature of node D. The same for D and B gets to a neural network, gets forwarded to a neural network, and this neural network generates the feature of the target node, which is node A. Applying the same mechanism here for our topology, we can aggregate all the feature of the real network, the real nodes in the network, and then we generate the feature of the unknown node, which is the intermediate nodes, as we can see here, that represents the traffic in each direction. As we can see, for example, the traffic that's going from autonomous system 100 to autonomous system 100 and distant to autonomous system 100, this should be allowed or disabled. The same for the traffic that's going from here to there and distant to autonomous system 500. After applying the first round of GNN, we verify the results using the validator. If the validator find out that this generated output fulfills our requirement, we generate final configuration. Otherwise, it calculates a reward that represents a calculated result, the calculated output, and then forwards this rewards to the evolution strategy optimizer, which tunes the neural network parameter in order to forward the network to achieve the optimal solution. A brief overview of evolution strategy. As we can see, evolution strategy is very similar to hill climbing. It's basically generate a random sampling of a set of solutions, and then from this sample of solutions we calculate the reward or the fitness of each sample, each solution, and then we calculate the gradient and we calculate the direction which we can enhance our reward, our fitness, and then we recalculate the parameter of the new distribution of the solution, and we again generate random sample of this new random distribution, and we keep doing this step until we reach the optimal solution. As we can see here, ES doesn't use back propagation, which makes it a good candidate for us because it enhances the calculation time, and it reduces the computation overhead because it basically uses transfer between the epoch, basically the distribution parameter, and not a full array or vector of the error vector. So here is another simple example to illustrate the whole process. For example, we start with a simple topology of 4 nodes connected in a star topology, and we started with the intent, as we can see here, that one can reach 2, and autonomous system 1 can reach 2, 3, 4, and at the same time we need to isolate autonomous system 3 and 4. So first we take this network and we represent it in the GNN topology, and this GNN topology we represent the main node, the original node, and we add an extra nodes for each link, one per direction, like as we can see here, A and B for the link between AS1 and AS2, and then we've taken the intent from here and we encode it in the node, as we can see these labels here, and then we collate these labels and we generate a feature vector for each node. As we can see, it's a identity matrix, and then we apply the GNN, the training for the GNN, semi-supervised training for GNN, and then we generate the output of these intermediate nodes, which were unknown for us. And then we validate the output for the intermediate nodes. After validating the output, we either write the configuration or invoke the evolution strategy to enhance the output of the network. And we keep doing this step until we reach our optimal solution. For the experiment results, we conducted 3 experiments to validate our results, our algorithm. The first one to validate the functionality of DeepBGP. As we can see here in this topology, we have this input as an intent, and then we applied our algorithm and we generated this output, which we have taken and applied in a network simulator, and we measured manually or tested manually all the connectivity between nodes and all the route preferences. As we can see here, for example, at router C, it prefers going to autonomous system 200 through router B over going directly through its link, maybe because of the cost or any other factor. And this is clearly here that the route from router C to autonomous system 2 is over this path, is over to autonomous system 2. One is over this path, which is 10, 10, 2, and has a higher local pref value. Another experiment, we also in the first experiment we tested that compared the result between using evolutionary strategy and deep Q learning. Deep Q learning for as an example of the deep reinforcement learning. As we can see here that ES strategy has evolved faster than the deep Q network, as the evolution strategy takes about 60 epoch. However, for the deep QN it took about 70,000 epoch, training epoch. Additionally, for the scalability analysis, we also performed another experiment using a randomly generated network with a random number of nodes, and we have seen that the network is the training time increases linearly with the number of nodes in the network. Also, we have noticed that the training time increases exponentially while using CPU. And in order to validate this, we wanted to verify which process is responsible for this exponential behavior. Therefore, we performed a third experiment to compare the behavior of the two main culprits in our algorithm, basically, namely the feed forwarding time or the validation time. As we can see here, the feed forward time is the main culprit here that causes this exponential behavior, which could be enhanced using hardware acceleration like GPU or TPUs. And for this concludes our work. As we saw, we introduced DeepBGP that uses neural network to generate with certainty network-wide BGP configuration. We also demonstrated that neural network has the potential to be used in network configuration synthesizing, and we experimentally illustrated that hardware acceleration and ES enhances the execution time. For future work, we are aiming at scaling DeepBGP to large network topology, and we also want to accelerate the training process using meta learning. And in addition, we want to generalize DeepBGP for other network protocols like interior gateway protocol or access list control. Thank you for your time, and I wish have a nice day.